Welcome to our lesson on rational expressions, or what are more commonly referred to as fractions. First, we'll start off with just a simple definition and looking at the domain and range. Right? Anything that has basically two polynomials, top and bottom, are considered a rational expression. It can be something as simple as 1 over x, where the top is actually a polynomial, it's just a special polynomial, just the number 1, or it can be something more seemingly complicated like this example of x squared minus 9 over x squared plus 3x minus 4. It doesn't matter what it is, as long as we've got, some stuff on the top and bottom of our fraction that aren't just numbers. It's not just 1/3 or 7/8. We call it a rational expression. Okay, you might remember that we can never divide a number by 0. So just like how having 3 over 0 is no good, right? Doesn't equal anything, it's undefined. This is no good if the bottom equals 0, right? We can't let the bottom equal 0. So when we're dealing with rational expressions, we always have to worry about the domain, and the domain is everything that we're allowed to plug into something. Remember, these are just functions, right? Because x can take on various things, various amounts. So we need to make sure that we don't allow x to be any numbers that will make the bottom 0. So in order to define the domain, you have to set the bottom equal to 0 and solve. Here's what we did here. We set the bottom equal to 0, which means when we're dealing with a quadratic like this, right, a polynomial of degree 2, the best way is to try and factor it. And then we know that if this is equal to 0, each of the terms is equal to 0. So either x plus 4 equals 0 or x minus 1 equals 0. You set each of those equal to 0, and you finally solve and figure out that x is negative 4 and 1. Those are the two values that make the bottom 0. So our domain is going to be everything except for those two numbers. It's just that simple. Another example. This one's already factored for us, so we know the domain is everything but negative 3 and positive 1. Okay. Next, lowest terms for a rational function. If you have to find the lowest terms, that's just a fancy way of saying, can you simplify it, right? Factor out everything they have in common and then divide them away. In this particular example, both polynomials had the factor 2x minus 5, and so you can simply cancel those, right? Whenever you have something top and bottom of a fraction, as long as it's being multiplied, right? That's the big thing here, is that it's being multiplied. This times that, this times that. And if it has multiplication, not addition or subtraction, but only multiplication, then you can divide it out. Another example, factor out everything as best you can, and you see that you have an x minus 4 on top and a 4 minus x on the bottom. But 4 minus x just equals x minus 4, that's a 4, times negative 1, right? Because if you multiply this by negative 1, you get negative x plus 4, the minuses cancel, and if you rearrange that, that's just 4 minus x. So that's what's going on here. You have to recognize that when you see a minus b, it's the same thing as b minus a times negative 1. So you always want to keep your eyes open for those kind of little sneaky maneuvers where there actually is something to factor out that you might not see when you just look at it originally. With that in mind, we know that we can take away one of the x minus 4's top and bottom, which is why we're now left with just one of them, right? We basically ended up canceling that, making it a 1. Here we're just reminding ourselves that we could list this either way. We can list it like this, or, right, so we've got a negative out in front, a negative on the top, or distribute the negative all the way through and list it this way. This is probably the cleanest, best way to do it, and that's going to be the way that you're probably going to want to do it for most of your homework and quizzes. Okay, how about some more operations? Simplifying. Well, we've already seen that simplifying just entails figuring out what they have in common and reducing. And that's what we're doing here with these two examples. We figure out if they have some factors in common, we cancel those out. In the example on the right, not only do they have the factor a plus b, but they also have some constants, right? They have a 3 and a 12, and that little red 4 is just reminding you that when you divide by 3, the 4 is left over. And then now you just have the 3a minus b, right, because everything else canceled on top, and then on the bottom 4 times a minus b. And yes, I would leave it like this. You might as well leave things factored out rather than writing it as 3a minus b over 4a minus 4b. The reason why is there might be something else you need to do to this. You might need to graph it. You might need to solve for various things. You might need to multiply it by something else or divide something by it. Other operations, and it's always going to be easier if you leave it factored out. Everything will be easier if you leave it factored out. Another example, very simple, right? Because we're dealing with multiplication, we can factor it as if it was one big piece. Factor the right, the left is already factored for us. We find things that they have in common. We've got this x plus 2 here and the x plus 2 there. Now in this step down here, because this is multiplication, they combined everything and they just put all 3 of those pieces on top and all 3 of the other pieces on the bottom, and then they ended up canceling those 2, but it doesn't really matter, right? The same thing, right? You cancel those 2 or those 2, you're going to get the same result in the end. And again, you'll notice that they left the answer factored. Another example, here we just have kind of some simple terms, powers of variables, in this case z. You bring them together. Now, I wouldn't recommend doing 6 times 28 and figuring out what that big number is, and 7 times 9 and figuring out what that big number is. Instead, do this idea of factoring the numbers out, right? The 2 times 3 came from the 6, the 4 times 7 came from the 28. That tells us the 7's will cancel, the 3's will cancel, and all that's left, right, once we cancel these things out, 3's cancel, 7's cancel. 2 times 4 is where you get the 8, and then you just have the 3 left over. With the z to the 6 and the z squared, if you want to do this, this is fine, but once you start to realize how powers work, right, you know that x to the n over x to the m just equals x to the n minus m. The top power minus the bottom power. So 6 minus 2 leaves you with 4 on top. Another example here with a little bit more complicated looking stuff because we have polynomials, but the idea is still the same. The technique is still the same. Break it up into its factors. So just like before when we broke it up into its factors, meaning just numbers, right, 2, 3, 4, 7, and powers of z. Now when we break it up into factors, it's things like n plus 2 and 2n minus 1, etc. Once you have it all factored out, then you can just cancel what they have in common. As you can see, we've got the 2 blue ones here, the 2 red ones there. Those will both cancel, and you'll just be left with what's left. Another example, again with bigger, kind of more complicated looking polynomials, but the theory is still the same. You'll notice the very first step we did here was we turned a division into multiplication. Recognize what's happening here? Originally, we had yellow over green, but we had division, right? To turn that into multiplication, you flip and multiply. You're multiplying by what's called the reciprocal. So now all of a sudden we have green over yellow. Now we've just turned a division question into a multiplication question. We're doing the exact same thing we did with this example. And we factor everything out, see what we have in common, and get rid of them. You'll notice that in this case, we're getting rid of something that is on each side of the multiplication, because when you have multiplication, it really just becomes one big string of things. And so you can reduce across multiplication. So those two will reduce, those two will reduce, the green things will reduce, the two z's will reduce, and wow, all of that factors down to just simply z over 3. Another example, back to multiplication. I think at this point you're starting to get it. Step 1, factor everything out. Step 2, get rid of what's left. Step 3, just write what's left over, right? So what you need to practice is factoring. That's key. And everything else is pretty basic. Okay, adding and subtracting rational expressions, really the same idea as adding and subtracting fractions. In order to add and subtract fractions, they have to have a common denominator. So they're going to talk about finding the least common denominator. And you can always find the least common denominator, but you can also always just find any common denominator, and then at the end, if you have to, reduce using the same techniques that we used here and in all of our other examples, where once you have your final product, your final answer, you just factor it out and go, okay, do they have anything in common? Can I reduce it? Okay, if you find a least common denominator, that step you don't need to do it, but sometimes it's easier just to find a denominator and then reduce later. Here's an example where we need to add these two polynomials. To find that least common denominator, or really to find any common denominator, you really want to be able to factor. So once again, factoring is key. You factor the left denominator, you factor the right denominator, you see what they have in common, you see what they need, and you realize that to have a common denominator you need this piece, that one's already there, and that piece. So you have 3 pieces. And once you have those 3 pieces, all you have to do is put the appropriate missing ones on each side. Here's another example. If we take those numbers, factor them out, we can see what they have in common, right? They both have a 5. They both have a z squared. This one just has 2 more in it, right? That has z squared times z squared. So we're going to need the 2, we're going to need the 3, we're going to need a 5. And if we take a z to the 4th, it has that in it. So that's what we take: a 2, a 3, a 5, a z to the 4th, and that's what we need right there. Now you just have to figure out, what do I have to multiply each piece to get it there? Well, to get a 30, I just need a 3 on this one, I need a 2z squared on that one. Finally, common denominator, add everything together, you're good to go. Another example here, you hopefully remember, hey look, m minus 5 and 5 minus m, I remember those the same thing. All I have to do is multiply one of them by minus 1. So go ahead and multiply the right hand side by minus 1. Now you've got a common denominator and you have a very simple answer. Don't forget that because of multiplying by negatives, you can really list this thing 2 ways. This way or this way. Which one is correct? It's really up to you. There's no rule as to which one of those 2 is better. A third example, one that's already been factored out for you, makes it a lot easier to find that least common denominator. Multiply the appropriate pieces on each side, and you're good to go. Again, you'll recognize that we leave everything factored. It just makes our life easier. The last type of rational expressions are what are called complex rational fractions, and those are just fractions inside of fractions inside of fractions. It's like a nesting Russian doll of pain that we all hate, right? So there are 2 different ways you can do these. Method 1, I don't really recommend. We'll go through one example, but I'll show you method 2 in more detail because I think it's the easier of the 2. In method 1, you're trying to find the least common denominator for everything, right? In this case, you have 4 expressions, but what if this had 6 or 8 pieces? What if this was something like 1 plus 1 over x minus 2 over y times x all over 3 plus 2 over x squared minus 5 over y squared. Now all of a sudden you got 6 pieces and you got to come up with the least common denominator for all 6 pieces, and it just gets to be a nightmare. It's an okay method when you have relatively simple complex rational expressions, like this one, where you only have 4 pieces. And when they say 4 pieces, they mean here's one piece, here's another, here's another, here's another, right? Things that are separated by minuses and pluses. What are called terms. When we talk about a polynomial, each term is separated by plus and minus. So in this case, we have 4 pieces. You look at the bottoms of all of those, an x, a y, an x squared, a y squared, and you see that x squared, y squared is the smallest number that encompasses all of them, right? It's the smallest, least common denominator. If you multiply top and bottom by that least common denominator, you haven't changed its number, right? If you multiply by this, you're multiplying by 1. But when you do that, it gets rid of fractions. Because when you take x squared, y squared times 1 over x, it cancels one of the x's, and that's where you get this term, xy squared. And then when you multiply by this piece, it cancels one of the y's, and you get plus x squared y. Do the same thing on the bottom. You get y squared plus x squared. On the top, we factor out. On the bottom, we can't factor anything. And the only reason why we did this was to check to make sure something doesn't divide out, right, top and bottom, and it doesn't, so this is our final answer, and we should leave it factored out. So that's method 1. It's okay. I think you're better off using method 2. In method 2, you just kind of do it in steps. Instead of trying to find a least common denominator for everything, you just find least common denominators for each half of the fraction. And when I say each half, I mean the top half versus the bottom half. And in fact, the nice thing about this technique is you can take something that looks relatively scary, oh, this big, huge, complex, ugly fraction, and break it down into manageable pieces. When you look at the top half, deal with just the top half. So instead of doing all of this at once, do just the top and go, all right, I need 1 plus x plus 1 over x plus 1 over y. I want that to be one fraction. I need to make that one fraction. So in order to do that, I need y over y here and x over x here, which gives me y plus x over xy, right? Y plus x over this common denominator. And that's the top. I'm done. Now, do the same thing with the bottom and go, okay, 1 over x squared plus 1 over y squared. Again, what kind of common denominator do I need? Well, I got to have both pieces, right? Y squared over y squared, x squared over x squared gives me y squared plus x squared all over this x squared y squared. And now that's the bottom, and I'm done, with each half. And now I have this piece divided by this piece, which means I have this piece times its reciprocal, x squared y squared over x squared plus y squared, right? All you do is flip it and it becomes multiplication. And then you go, hey, look, these things cancel. The x times y cancels out the powers, and I'm left with just x plus y. That's this piece here. I rewrote it in alphabetical order. Times xy all over x squared plus y squared. You go, hey, look at that. Same answer they got. Okay? So rather than trying to do it all at once, where you're going to make mistakes, because you're going to try and do too many things at once, give your brain a break and take it in little manageable bite-sized pieces, and then bring those pieces together at the end. It's a much better technique. It's the one I would recommend doing. Okay, that's it.